Hi, thanks very much for this chance to talk. I'll be telling you about fairly new work by Rahul with Narayanan Menon and Rama Govindarajan. You can read about it there. And, sedimentation actually is a problem in statistical mechanics, so I feel I'm allowed to talk about this at this meeting. It has a very honorable history, including Smolensky and Einstein and so forth, so I'm not too worried. I've sort of been interested in problem in various forms for a long time, and I'll start with background on early interest and tell you about some new work we've done, and then tell you about some particularly amusing dynamical aspects of it, and I'll summarize. Okay, so you know that in fluid dynamics, for sufficiently slow flows out to a reasonable length scale, you can forget inertia, you can forget accelerations and advection, and the problem reduces to solving for the velocity field given boundary conditions under the condition of incompressibility, and if there are force densities, including those force densities in the problem. So for example, in that limit, you know that if you have 1 point force, that is one settling particle, its velocity field decays as 1 over r, which means that a bunch of such settling particles are as strongly interacting as a bunch of electric charges. So it's a very strongly coupled long-range interacting system. Even at the level of 3 particles, it turns out it's rather interesting. Unfortunately, the particles are settling upwards here, so think of them as bubbles. There was a numerical study by Yanossi who showed that 3 particles settling together will hang about together for a while, and then 2 will join up and the 3rd will break off. But exactly when that happens is infinitely sensitive to initial conditions. So even 3 sedimenting particles is chaotic. And you can actually watch that happen in Rahul's experiment. So here's 3 disks settling. I won't show you multiple initial conditions, but there you are. You see them pair off. Okay, and so therefore, sedimentation is a rather non-trivial statistical physics problem. There's a long history to it about velocity fluctuations, about what the steady state really is, and so forth. I will not talk about that today. What I'll tell you about is a few elementary pieces of the dynamics of settling particles. If you have 2 particles, then if they're slightly closer together, if you bring them closer together, they settle faster, essentially because there's less fluid flow between them, so you reduce drag. And if they are separated in the vertical direction as well, then they don't settle straight down, they settle in part laterally. Okay? It's important to note that in the Stokes limit, these 2 neither approach nor recede from each other, and this vector neither decreases or increases in length nor changes its direction. The pair drift jointly. This is a consequence of the reversibility of Stokes flow under reversing time and reversing all external forces. The result of this is a rather interesting instability. If you have an array of spheres, I don't know which of these is the best, but I'll show you one. So Rahul, this is what you can see is that the guys in the middle fall a little faster, the tilted bits move in together, and so there is this instability. And you can do this for a very long array, and you find rather interesting dynamics. And this actually gave rise to a nice collection of problems in StatMech a long, long time ago called strong phase separation, in which several friends, I don't know if Mustansir is around here, no? No, okay. Anyway, so it's a fun class of problems. So a settling array of particles in a viscous fluid. So the thing to do though is you have to choose your viscous fluid correctly. If Rahul initially picked a fluid that was supplied a fluid by the company that is 10 times too viscous, so he would have taken 50 years to do his PhD. So luckily he realized this well in time. And one question is this. In principle, the underlying mechanism is just this, right? If these particles are slightly closer together, this guy settles faster. Now you've got a tilt. The tilt gives rise to an inward motion, and therefore you clump. But on symmetry grounds, an object that's tilted like this could as well move outward as inward, right? Nobody told you that something tilted like this has to settle like this. You could imagine some general dissipative system in which it drifted the other way. If that happened, you would get what turns out to happen, at least theoretically, in arrays of flux points drifting through a slab of type 2 superconductor. And there what happens is increasing density, move faster, you have these tilts, and these tilted bits move outwards. So if you compress a bit, a little wave travels, if you pluck it, okay? This has not been seen in flux lattice systems in experiments, but in principle you could ask, is there something you can do to the hydrodynamic problem of particles settling in a fluid to make it do something like this? And spoiler alert, yes there is. Whereas when an array settles, as I said, increased density, settle faster, tilt, move together, something can compete with it. If your particles themselves are elongated, then the fact that one tilted particle moves, settles gravitationally with a component that way, means that if you have an array of ellipsoids or disks, then, yes? Then the tilted region, although the line of centers effect is making it move inwards, the natural drift of the individual particles can make it move outwards. So depending on the ratio of the lattice spacing to the particle size and so forth, you can imagine escaping this seemingly inevitable instability. It's important to note in this dynamics one funny feature, which is that you've got a vertical direction, you've got elongated particles. Normally, if you define a direction, you have an object with an axis. That object should have a preferred direction at which to orient, with either parallel or perpendicular. You know this from liquid crystals. But if you have a symmetric ellipsoid in gravity, settling under gravity, it doesn't care at all, because all that matters is the location of its center of mass. So if you've got an apolar ellipsoid, there's a kind of higher symmetry in the problem. There's like a zero mode for the orientation with respect to gravity. And this is a rather amusing fact. It's a totally non-obvious fact, which plays some role in what we'll say. Okay, anyway, so now you can build the pair dynamics. So you have these two particles. If they're tilted at an angle theta, there's a horizontal drift proportional to sine 2 theta. If they come, if two of them come closer, if they're vertically separated, then their vertical speed changes, but it doesn't matter if they're like this or like this, hence squared. If they're like this, you get a horizontal drift proportional to sine theta, cosine theta. And if you have two particles separated by some distance, the flow field of each one rotates the other one. Okay? You can put this together. And so it won't go back for some reason. We discussed this in the context of just two particles settling and found some rather amusing physics in which the dynamics of the settling disks, the coupled dynamics of the orientation and the separation were exactly like Kepler orbits. You can read about that there. In any case, now you can build the dynamics of a whole array. And you can actually take into account the hydrodynamic interaction of each particle with particles not just adjacent, but a distance L times d, where L is 1, 2, 3, etc. Right? So you can sum the hydrodynamic interactions and build the equations of motion for the horizontal displacement, the vertical displacement, and the angle.
What are the initial orientations?
So, no. So this dynamics, because you want to use a displacement field, is with respect to a regular periodic reference lattice.
All parallel orientation.
So you can put in other things, but let's say all parallel vertical, all parallel horizontal. You can also look at other cases. So the answer indeed depends on which of these you look at. But you could imagine a physical system in which the particles have been prepared. They have some little flexural springs, and therefore this is their natural orientation, and you can look at the dynamics of that. So you can write this down. What we did was to truncate it nearest neighbors, because for the experimental system that I'll show you, that's appropriate because there are walls. And the fact that the angle equation doesn't have any term that reorients the angle with respect to the vertical is because of this symmetry that I told you about. And it's a nice dynamics. It's, in some ways, if you look at theta dot being second derivative of ux and ux dot being something like theta, theta looks like a momentum. There's a system with no inertia, but a tilted object has a tendency to drift horizontally because there's gravity. So its tilt acts like a momentum. And it's an interesting problem also because its dynamical matrix doesn't commute with its adjoint. And it has funny properties as a result. And so you see a stunning variety of behaviors, including essentially the old instability that you saw with spheres, modifications of it, and ways in which the system resists it. So since I have to finish talking soon, These are the kinds of behaviors you see. The most interesting is that you see that their disks, you can see these guys are tilting outwards, and therefore they're trying to move apart, resisting the tendency to clump. I mean, they resolutely resist the tendency to clump for a long time. So you can indeed completely wipe out at this linear level, you can kind of completely wipe out the famous Crowley instability of settling disks. The lines are just, the centroid of each. But if you look at a large array and you look at fairly dense, then you get rather striking instabilities whose nature still bears discussing. But let me, since I should really stop talking, how much time? So this is a sort of linear stability diagram, and these are experimental points, which agree very nicely. But what I want to focus on is this. That I told you the dynamical matrix is non-normal. What that means is linear stability analysis doesn't tell you the full story of what the system can do. Depending on the initial perturbation vector, your magnitudes of the variables can grow for a while before eventually giving in to the fact that the eigenvalues have negative real parts. That transient growth can take place long enough that the system enters a regime where your linear theory is no longer good, and all kinds of wild things can happen. In this system, we are actually able to predict the form of those, and we are actually able to measure the transient growth of the amplitudes. And first of all, we are able to predict the dynamics of the wave-like excitations that come out. First thing is that you actually have waves. The solid line is theory, the dash is simulation, and the colored things are experiment. So we are actually able to do a fairly complete theory of the system. And so this is a system in which it's really in your face about linear stability analysis, not telling you the full story. We thought we had found a system which would lick the Crowley instability. Instead, what it turned out to be was a nice playground for transient growth phenomena. And is that the end or question end? End. Okay, yeah. Okay, so it's interesting. One sort of nerdy, pedantic point is that the orientation variable, the fact that you've got gapless modes is because the orientation doesn't have a preferred doesn't get damped out to either horizontal or vertical individually, which means it's acting like the orientation treated as a momentum has a weird kind of conservation law. And so even though it's a configuration-like variable, it's acting like a momentum. So which, for people of my upbringing is somehow terribly charming. The dynamics is fun. You can watch it forever, and I'll let you watch it. Oh, I can't do that. I have to stop. Anyway, and so I'll just summarize here. So I've shown you that we can build linearly stable sedimenting arrays. We can show you underdamped waves in experiment and in theory. Non-normality eventually takes over and does rather stunning things. We don't know if you introduce aligning interactions among the disks, whether you can actually get totally stable arrays. If the particles, instead of being disk-like, are cone-shaped, then this deal that they don't care about their orientation, that's off. Now they do. And so that will damp all of this. And finally, what is the overall statistical mechanics of a collection of settling disks? I should emphasize, by the way, I didn't tell you, these are big particles, centimeters, millimeters, centimeters in size, and they have a random component to their motion because of these instabilities. So eventually they act like they have diffusion, but they're not Brownian at all. These are really big particles. So this is statistical mechanics of systems in which the bath has nothing to do with thermal physics. It's a completely non-equilibrium bath created by the interacting dynamics of the particles themselves. Okay, thank you.
We have time for a couple of questions.